Alrighty, graphing rational functions. Um, Rational functions are functions that have the x variable in the numerator and in the denominator. So for example, it could be an equation or a function like this. But usually, to graph the rational functions, you will need to put it in factored form, because putting it in factored form makes the properties show up a lot clearer. So we could factor the numerator is already factored, so we just factor the denominator into x plus 3 and x plus 2. And there are a few key points in a rational function. There is the vertical and horizontal asymptote. There is a hole, if there is a hole. And yeah, I think that's the general gist of it, to be honest. To tell where the vertical asymptote is, that is a factor in the denominator that is only in the denominator. So in this case, it's this one over here. And we could find what that x value is. It's x plus 2 equals 0, and x equals negative 2. So based off of the function, we could already tell that the x is equal to negative 2. So just to write that here, the vertical asymptote is a factor only in the denominator. Alright, and for the hole, we could tell where the hole is because it is a common factor in the numerator and in the denominator. So in this case, the hole is this factor x plus 3, and we would set it equal to 0 because a hole or a vertical, like in this, we also set it to 0 in the vertical asymptote. We set it to 0 because in a vertical asymptote, or in an asymptote in general, or a hole, that is where there's no y value for like designated x value. So let's look at this rational function, graph of this rational function as an example. You can see that these values are approaching the asymptote, but they're not actually reaching it. So, or we could look at it in the vertical asymptote. It's because we found that x is equal to negative 2. Then when we plug negative 2 back into the function, negative 2 plus 2 equals 0. And when we have a 0 in the denominator, that's being multiplied by another value, then or just when you have a 0 factor in the denominator, then the function is undefined. So in this case, when we have a hole, that is when instead of having an asymptote, it's just like a literal hole in the function. Alright, now when we try to find the horizontal asymptote, there are actually 3 ways to find it depending on the degree of the numerator and the degree of the denominator. So in this case, the degree is 1 over here, because if x doesn't have a exponent mentioned above, it will be 1. And we could have the highest degree in the numerator be the variable m, and have the highest degree in the denominator be the variable n. So in this case, this function has m less than n, 1 is less than 2. So this is one possible way that could occur. In this case, the horizontal asymptote would always be y equals 0. If you know anything about limits, that proves why y equals 0, but for now, just remember that when m is less than n, then y always equals 0. Another possible function could be when m equals n. Like it could be like this, for example. because 2 is equal to 2, then m is equal to n. And when m is equal to n, you look at the leading coefficient of the degree of the highest degree term in the polynomial. In this case, they're both just 1 and 1. But you could have some examples like, I don't know, for example, 5x squared plus 7x plus 11 over 2x squared plus 9x plus 15, for example. And if you look at the leading coefficient, it's going to be 5 over 2, and that's what the horizontal asymptote is going to be. If we look at it in a variable form, like in a formula, it could be ax squared plus bx. It could be like, no, just to simplify it, it would be like ax plus blah 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 plus c over bx plus blah 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 plus d, and this would be x to the m and x to the n. So look at it over here. The a is the leading coefficient of the numerator's highest degree term, and the b is the denominator's highest degree leading coefficient. So the formula for the horizontal asymptote when m equals n is y equals a over b. Alrighty, and the third example for you to find a horizontal asymptote, well, in this case, it's not really a horizontal asymptote, it's more of a diagonal asymptote, and this is when m is greater than n. So for example, the function could be 2x squared plus 11 plus, I don't know, like 13, just some for the sake of the example. And in this case, we would actually use long division, and we would use the quotient of the long division. Actually, no, I don't think it's the quotient. It's when you divide this by this, and the actual value that you get from that is the slope is the value that we will use. So I'll just guide us through it. So it'll be x plus 5 divided by 2x plus 11x plus 13. So in order, if you know how to do long division with polynomials, you can continue on. But if you don't, you should probably watch another video to figure out how to do it. But to divide, it takes x times another 2x to reach the 2x squared, or multiply the 2x plus 5 to get 10x, and we subtract both of them to cancel this out, and this would be x. Drop the 13 down, and 1 times x would bring us to x, 1 times 5 would bring us to 5, and this would cancel out. This would be left with 8. So it turns out that the diagonal slope only requires this section, not the remainder. So in this case, the diagonal slope would be y equals 2x plus 1. Alright, let's do an example. So this will have a function of 2x over x minus 3. So what we can see here is that the exponent of the leading term in the polynomial for both of them is 1. So this is a situation when m is equal to n. And if this is the case, then the horizontal asymptote is when a equals b. So if you remember from the previous minute or so, I showed you that the original structure of the rational function is something like this. So, this isn't supposed to be a, this is supposed to be b. And when m is equal to n, that is when the horizontal asymptote is a over b. And once you get to limits, again, that is where you actually prove this type of stuff. But right now, These are just some of the stuff to just get a grasp of. And in this question, A is 2 while B is 1. If it doesn't show, it's 1. So the horizontal asymptote would be y equals 2 over 1, which is 2. Now another thing we need to find is the vertical asymptote. And the vertical asymptote is the factor that is only in the denominator. And in this case, it's x minus 3. That's the factor. And we would set it to 0 because that is when the denominator would be undefined, and that is when x equals 3. So when x equals 3, and we substitute in 3 for here, it'll be 3 minus 3 equals 0 in the denominator. And when 0 is in the denominator, the function is undefined. So, and also another thing we could find is the whole, but because there's no common factor in the numerator and the denominator, we don't need to find a whole. So the next thing we need to do is to graph out. It's to make a table before we graph. So we can start with some values like 1, let's do like -1 to go left, and then 2 and 4. But I think like a good thing we could do is to draw out what we have at the moment to give a general to give a general idea of what points we should use. Alright, so the horizontal asymptote is at x plus 3, and the vertical asymptote is at y equals 2. So we would want to have 2 values to the left of the vertical asymptote and 2 values to the right of the vertical asymptote. So we have so we can also add 5 in here as well, so we have another one to the right of the vertical asymptote. So when we plug in 0 into this equation, it'll be 2 times 0, which is 0 over 0 times 3. And when 0 is in the numerator, the value would be 0. And for the rest of these, I'll plug it in, but you could do the math on your own. Or for the last one, 2 times 5 over 5 minus 3, that'll just be 5, I think. Alright, so this is the chart. We should also add an extra value here to accommodate for the 5. And now we plug the points in. And now we just connect the dots. And that is our rational function for this problem. Alright, let's do another problem with a different scenario. In this case, it'll be f of x equals 5x over x squared plus x minus x. In this case, this is 5x to the first, so because the exponent for the leading term in the polynomial in the numerator is less than the one in the denominator. 1 is less than 2. This is a situation when m is less than n. And when m is less than n, that is when the horizontal asymptote is y equals 0. And we can also factor the denominator out into x plus 3 and x minus 2. And over here, we have 2 factors that are only in the denominator. So this means we have 2 vertical asymptotes. So the vertical asymptotes would be when the x is when this factor equals 0. So that'll be x plus 3 equals 0. That's when x equals -3. X minus 2 equals 0. That's when x equals 2. And those are the 2 vertical asymptotes. there aren't any holes in here because there's no common factor in the numerator and in the denominator. So we'll leave it at this. Before we graph, we could also sketch out a chart, and we could also make a graph over here as well to sketch out the basic horizontal and vertical asymptotes. Alright, let's graph the vertical asymptotes. That is when x equals 2, and this is when x equals -3. So in this case, we would probably want points in the middle and the left and the right. So based on the values we got, we could use 1, 0, 1, -1, 3, 4, -4, and -5. This is just based off the notes that I did on this problem, and I'm just gonna fill in the values here. So right now we just plug these values in. And after we plug it all in, we're just gonna graph it out. And yeah, that is what happens when m is less than n. Alright, last scenario. This is when m is greater than n. So this will be the function that we would use for the example. And because 2 is greater than 1, m is greater than n. And in this case, instead of having a horizontal asymptote, we'd have a diagonal asymptote. And that is when we divide this and whatever comes up on top is the is what equals to y. So it will be x minus 2, and here will be the numerator, and we would solve for this. So to get to x squared, we have to multiply x by x, and -2 times x would give us -2. We subtract both of them, and this would give us -x. We drop down the 8, and over here we need to get to -x, we multiply x by -1, and -2 times -1 is +2. Oh, and if you haven't gone through dividing polynomials with long division yet, you should probably watch another video to see how it goes first, because I'm just going through it right now. And this will be and we ignore the remainder, so what comes up on top is the diagonal asymptote. So y is equal to -x plus 1. That is the diagonal asymptote. And we have factor in the denominator over here. I don't think the numerator is factorable, so we'll leave it as that. So the vertical asymptote is when x is equal to when x minus 2 equals 0, and that is when x equals 2, and this is the vertical asymptote. And now we could graph out the general gist of it and prepare a table to plug units in to see the general gist of the graph. So the diagonal asymptote is when x is equal to -1, and this is the graph of that's when x is equal to -1. And the vertical asymptote is when x is equal to 2. So now we could draw a table and plug values in. These are the values I used in preparing this example. Now I'm just going to plug the values in. But a good rule of thumb again is to have two values to the at least two values to the left of the vertical asymptote, and at least two values to the right of the vertical asymptote. And if there's multiple, like the previous example, you would want to have at least two left and at least two right for each of the vertical asymptotes. So I'm gonna continue on with this, and let's plug these points in. Yep. Alright, and this is the rational function when m is greater than n.